Hi everyone. In this video we're going to look at Vieta's formulas. These formulas apply to polynomial equations, and the polynomial can have any degree at all, but in order to understand the formulas we're going to take a look at the degree 2, 3, and 4 cases, and we will establish a pattern that you will see applies to higher degrees as well. So let's start with the degree 2 case. If the roots of ax squared plus bx plus c equals 0 are r1 and r2, then the sum of those roots, r1 plus r2, is equal to negative b over a, and the product of those roots, r1 times r2, is equal to c over a. Now, this is true for any two roots, real or complex, and even possibly repeated roots. So let's prove this to see why it's true. So if r1 and r2 are roots of this equation, then they are also roots of the equation obtained by dividing through by a, arriving at this equation. And we're assuming a is non-zero because this is a degree 2 polynomial. So that means that x squared plus b over ax plus c over a can be factored into x minus r1 times x minus r2. But we can expand that product, arriving at x squared minus the quantity r1 plus r2x plus r1 r2. Now if we equate coefficients, we see the coefficients of x squared on each side are 1. The coefficient of x on the left is b over a, and that must equal negative r1 plus r2, the coefficient of x on the right. Okay, well that implies that the sum of the roots is indeed negative b over a. Also, if we equate the constant terms, we find out that c over a is indeed the product of the roots, r1 times r2. Okay, let's take a look at what these formulas actually are in the degree 3 case. So here, if the roots of ax cubed plus bx squared plus cx plus d equals 0 are r1, r2, and r3, then r1 plus r2 plus r3 is equal to negative b over a. That's the sum of the roots, is negative b over a. Also, r1, r2 plus r1, r3 plus r2, r3 is equal to c over a. We refer to this expression as the sum of the roots taken two at a time. So we're taking two of the three roots, forming a product, and we're getting the sum of all of those products. Okay, and r1, r2, r3 is equal to negative d over a, which is the product of the roots. Notice you can get a little more symmetry here by calling the sum of the roots taken one at a time. And you can call the product of the roots the sum of the roots taken three at a time. Okay, and I think you can see the pattern already, even just looking at the degree 3 case. The negative b over a is the sum of the roots, and we're starting with a negative there. Then we're going to alternate signs and get a positive c over a as the sum of the roots taken two at a time, and then we're going to alternate back to a negative d over a to get the sum of the roots taken three at a time. So let's see, why is this true? We'll try to do this without doing too much algebra. Well, we're going to again divide the given equation through by a, and we end up getting the polynomial x cubed plus b over ax squared plus c over ax plus d over a. And the r1, r2, and r3 when substituted into this polynomial also produce 0, and therefore this can be factored into x minus r1 times x minus r2 times x minus r3. So let's see if we can explain this without actually expanding out the right-hand side, although that's one way to do it. If you expand out the right-hand side and equate the corresponding coefficients, you'll arrive at the formulas above. However, let's look at the coefficients of each term on the left one at a time, starting with the coefficient of x cubed, which is 1 on the left side. On the right side, there's only one way to get an x cubed, which is by selecting an x from each pair of parentheses and multiplying those together. In fact, the way you form this product of these three linear factors is you select one of the two terms from each group, from each factor, and multiply your choices together and add up all the possible choices. So the only way to get an x cubed term is x times x times x, and the coefficient is also 1, of course. Those coefficients match. But now let's look at the coefficients of x squared. On the left, you get this b over a. On the right, in order to get x squared terms, you have to choose x from two of the three linear factors and choose the constant term from the third. So the coefficient of x squared on the right-hand side would come from, let's say, selecting x, then negative r3. So that contributes negative r3 to the coefficient of x squared. But you can also select x, then negative r2, then x. So that contributes negative r2 to the coefficient. And you can select negative r1, then x, then x. So that contributes negative r1 to the coefficient. So that tells us that that is equal to the coefficient of x squared on the left, which is b over a. And if I divide through by negative 1 and rearrange, I get one of Vieta's formulas above for the sum of the roots. Likewise, we can look at the coefficients of x on each side of the equation. On the right side, in order to produce x terms, you have to select x from just one of the three linear factors and the constant terms from the other two when forming products. So you can take x times negative r2 times negative r3, and that contributes r2, r3 to the coefficient of x. Or you can take negative r1 and then x and then negative r3, and that contributes plus r1, r3 to the coefficient of x. Or you can take negative r1, then negative r2, then x, and that contributes r1, r2 to the coefficient of x. So that must be equal to the coefficient of x on the right side, on the left side rather, which is c over a. And that is one of Vieta's formulas, the sum of the roots taken two at a time. And finally, you can look at, let's call it the constant terms on each side of the polynomial equation. So on the right side, the only way to get a constant term would be to select the constant term from each of the three linear factors. So you would have to select negative r1, then negative r2, then negative r3, and form that product, and it would be negative r1, r2, r3. And that must equal the constant term on the left side of the equation, which is d over a. And so if I divide through by negative 1, then I get the last of the Vieta's formulas above for the product of the roots. So that's the way you look at this. And now we're going to look at just one more case, the degree 4 case, just to establish the pattern. We'll spare you the proof. But here's what Vieta's formulas are for this case. So if the roots of ax to the fourth plus bx cubed plus cx squared plus dx plus e equals 0 are r1, r2, r3, and r4, then we have the following. The sum of the roots is negative b over a. The sum of the roots taken 2 at a time is positive c over a. The sum of the roots taken 3 at a time is negative d over a. And the product of the roots, or the sum of the roots taken 4 at a time, is e over a, positive e over a. So I think you can see the pattern here. Each answer has a fraction that is either negative or positive with an a in the denominator, and the signs alternate. In the first case, we have a negative, then a positive, then a negative, and then a positive. And we just make our way down the polynomial from left to right. We do negative b over a, then positive c over a, then negative d over a, then positive e over a. The proof of this is very much like the degree 3 case we just looked at. And you can generalize this to any degree. So these Vieta formulas are useful for solving certain types of problems involving the roots of polynomials, and we're going to look at such problems in the future. Thanks for watching the video.